Hey everybody, how you doing? Dr. Helpman here, Tech Talk Education. In this video, I want to talk to you a little bit about how DNS works. I said in a previous video, it's one of the most tested pieces of software on the planet. It's used over and over again, millions and millions and billions of times a day. And it's kind of the silent, it just goes and goes and goes. And I wanted to talk to you about how it works. Let's get started. Now, while DNS is domain name system is what that stands for, while it is very common and used heavily every day all across the internet, it's easy to set up and configure in a smaller environment. As you might imagine, when things get a lot more complicated and we have a lot of DNS servers in the mix and things like that, it can get a little more technologically challenging. But this is probably some of the best tested code out on the web. So let's see what's involved here, how this works. So DNS stands for Domain Name System. A domain name, if you're not familiar with that phrase, if you've come out of the Microsoft Windows Server environment, you're familiar with what is called a Windows domain versus a Windows workgroup. That's not this domain. When we say domain name here, what we're talking about is a website like www.amazon.com, for example, is the name of a domain. And so you've got to get used to that. Now you can put things on the front of a domain, so you can have subdomains. For example, you could have mail.google.com, chat.google.com, or whatever it might be, and calendar.google.com, and so forth. So those are subdomains to a primary domain. Now, DNS's whole job is to translate domain names into IP addresses. DNS also keeps a reverse lookup table called in-address ARPA, and it can take an IP address and translate it into a host name, and that is another common use of DNS. It's not nearly as common as translating a domain name into an IP address, however. Now, TCP requires that you must visit a device on the internet, and we're going to call that a host from now on, because a host can be something other than a computer. It could be a phone, it could be a camera, a buoy on the ocean, whatever. If it's got an IP address, we're going to call it a host. And so we're required to connect to hosts via IP address. The problem is, domain names are easy for us to understand as humans because we understand words and putting them together and making sentences and things like that. Computers don't understand that. What they need are numbers which wind up turning into electrical signals. So let's take a look at this. We're going to go visit Amazon.com, and you can see what that looks like when we're getting the domain's IP address. So I have a command prompt here, and I'm going to just type in ping www.amazon.com. It's a very straightforward command. The Windows ping command only goes 4 times. Linux goes in perpetuity unless you set the T switch on it so that you can stop it after a certain number of times. There's a couple of things we want to pay attention to. First of all, you pinged a host name here called Amazon.com. However, you're getting a response here from this thing .cloudfront.net. Now, CloudFront is what is called a CDN, and we're going to talk about that in just a minute. And this is its IP address right here. And then we have a thing called the time to live that we're going to talk about as well. So ping is a really good way of pinging a host name in order to find out an IP address. But you should be aware that even though you think you're pinging Amazon, you're being redirected, and the thing that's responding here is this domain right here, and this is an Amazon AWS domain that's responding on your behalf here. Okay, so let's move ahead here. Now, why do we need DNS? We've talked about this already. Humans understand words and phrases better than long strings of numbers. Computers don't. Computers like numbers. These numbers are ultimately translated into bits and bytes. That's why we can use 2 or 3 different number series, decimal, octal, hexadecimal, binary, 4 number series. And these represent on or off inside an electrical circuit. And so as the data is traveling across the wire, it's really just pulses of either ones or zero bits going across the wire, whether it's light, Wi-Fi, Ethernet, it doesn't matter. The idea is that everything gets translated into ones and zeros to physically go across the wire. Now, the journey of a DNS query is this. You have a cache. Now, we've got to get used to this word cache. You could say cache, but we don't in the United States. A cache, you're probably most familiar with a cache of weapons. We're storing all these weapons for war or whatever, or a cache of gold bullion. But in this case, we're talking about a memory stick or somewhere in memory that's designed to hold repetitive things, and we have them in a variety of software applications as well as in the computer itself. So first of all, you have the browser cache, the browser cache. What happens is, as you're surfing and you go out to this place a lot, it's going to hang on to that domain name, and so the browser will do that for you. Your operating system also has a cache in it, and then it will cache certain hits. Now, if you can't find it in either of these locations, the next thing we're going to do is we're going to go to what's called a recursive resolver or a DNS resolver. This is very often provided by your ISP, or it could be a public DNS like Google, whose addresses are 8.8.8.8 and 8.8.4.4. And there's another famous company called Cloudflare. They have a DNS address 1.1.1.1. We'll learn about a couple of others. And the idea behind recursive resolver is that we don't know right now, so we go ask somebody else, hey, do you know how I catch the bus to Boulder, for example? And this person will be like, no, I don't know how you catch the bus, but maybe go over here and ask them. Do you know how to catch the bus to Boulder? No, I don't, but maybe go ask here. That's the idea. It just keeps going and going until it finds somebody that can actually respond to the question. Now, we will talk a little bit about these root servers. These are direct a resolver to the correct top level domain. So we've got this set of 13, they're called root servers. There's a reason for that. And so let's say that you're looking for this one-off little domain name. You've sent it, your browser doesn't know about it, your OS doesn't know about it, your ISP, for example, Xfinity or AT&T or Verizon, whoever, doesn't know about it. They pass it off to a root server, and then the root server knows how to direct this thing to the correct top-level domain server. A top-level domain is something like a .com or a .net or a .mil, .org, things like that. So there's all these different TLD servers that have a database of all the known coms and all the known orgs and things like that. So top-level domain servers we talked about, they point to the correct authoritative name server. Now that word means that you have found a server that has the authority to give you the correct IP address for a given host name. Authoritative name servers are the final source that hold the actual IP address of the domain. So the idea is, I don't know, I'll pass it off to my ISP. They don't know, they pass it off to a root server. They ultimately pass it off to a TLD server, and we get that information back. And now we can begin using an IP address to talk to the host that we want to talk to. Now let's talk about these particular, oops, I went too far. Let's talk about these particular root servers. There are several of them. And you can see that they have capital letters A through M. And the reason they're called root servers is there's a dot there. And I'll show you an example of this in just a minute. But if you look at the table, you can see the VeriSign is the only one that's listed twice. VeriSign Incorporated. These guys do a lot of digital certificates. They're a CA company. But they also are in the camp of doing these logical root servers. There's others, University of Southern California Information Sciences, Cogent, NASA Ames Center. There's a military one, the U.S. Army Research Lab. There's a really interesting company called NetNod. They're in Sweden. And these things are based all over the world. So we have a pretty good, pretty robust separation of servers around the world, I guess is the way that I would phrase it. You also have their IPv4 addresses, and you have their IPv6 addresses, and you need to remember that anything, it was mandated a long time ago now, probably been 15 years, servers like this, universities, government sites, military sites, must use IPv6. You don't necessarily need to, but your computer probably does get an IPv6 address, even though you're not familiar with it. So these are the root servers. And so what you would do is you would have a.verisign.net servers, and then it would point to this address here or this address here. So they're very, very interesting, these root servers. Now I want you to pay attention to this RIPE NCC. There are 6 or 7 of these things. Let's go take a look at them. Now these are called Regional Internet Registries, or RIRs, RIRs. I don't know how you pronounce that acronym. There are 6 of them. And the first one we looked at was RIPE, and is based in Amsterdam, and it serves the Central and West Asia, Europe, and Russia. So RIPE is responsible for that, and I keep going forward. I want to go back. And you can see here that RIPE is responsible for Europe. It's in the K letter. This is its IP address and its IPv6 address. There are others. There's the Asia Pacific Network. It's called APNIC. It was founded in 1993. It's based in Brisbane. Serves East, South, and Southeast Asia and Oceania. There is ARIN, which is based in Chantilly, Virginia. This serves us who are in the United States or Antarctica, Canada, or in some Caribbean countries. There's a little bit of a split in the Caribbean countries, so one RIR serves one and one serves another. There's the thing called the Latin American and Caribbean Network Information Center, LACNIC. It's based in Montevideo, Uruguay. It serves Latin America and some other Caribbean countries. So the Caribbean countries are kind of split. There's a thing that's an overall global management environment called the Number Resource Organization, NRO. And then the newest one is called the African Network Information Center. It's called AFRINIC, and it's based in Ebim, Mauritius, and it serves all of Africa. So these are what are called regional internet registries. These guys are the ones that are responsible for IP addresses in a given set of countries. Now, there are some key DNS players you need to keep in mind. You have DNS resolvers, which are recursive, meaning if I don't know, I'm going to go ask somebody that has the authority to tell me, which would be the root servers, who might know and who might feel the need, if it's rare enough, to pass it up the line to TLD servers. Now, why would that be? Well, if you register a domain today, and you're going to get an IP address, you're also going to be registered with DNS, but it takes a while to copy that information to all of these servers. A lot of times it's a couple of days, maybe 4 or 5 days, and so the idea might be that you can't hit it just now, but the record has been copied to a TLD server. So let's say that you register yourself as an org, that record winds up in the org TLD servers, but then maybe nobody else knows about it, so we have to do like a little forward search until we find that, then we cache it, and then we have it. Now, what does it mean when we say the term recursive DNS? There's a certain order that happens here. So in the context of DNS resolution, a recursive DNS resolver is one that A, accepts queries from clients. What do we mean by that? We're talking about client server. So that could be a browser, you going out to find a website somewhere. Could be an application that needs to get a hold of a website and do some work as well. For example, maybe you're buying something from Amazon, and Amazon passes part of the transaction off to a bank server, for example, or a credit card server. In other words, a recursive resolver doesn't have a complete database of all the names. It doesn't know the answer to every query. It needs to ask other DNS servers to help resolve the query, and then when the recursive resolver receives a query, it checks its cache first, and if it finds it, that's great, and if not, then it queries a root server or other authoritative server to get to the next hop. It might have to wind up querying and clear to the next hop, which would be a top-level domain server, authoritative server, and so on. And then it returns the final answer to that client. Now that sounds complicated, doesn't it? Like there's not a certain order to it. But in the scheme of things, there are companies that have these authoritative servers. So Amazon.com, of course, is big. Microsoft is big. Oracle's big. Google is big. So these would have authoritative DNS servers. Other companies, maybe not. And so we might wind up having a query clear through to a top-level domain server to find the IP address for that particular machine that we're trying to contact. Now, what is an authoritative server? In contrast, an authoritative DNS server has a complete database of a specific domain, i.e. Amazon.com, Microsoft.com, Google.com, or a zone. Now, a zone is an interesting phrase, and if you wind up getting into Windows Server administration for any kind of time at all, you're going to wind up working with what are called DNS zones. So a zone is a DNS database that is particular to a given organization or a given endeavor of some kind. It returns answers directly without needing to query other servers. Recursive resolvers are usually operated by internet service providers like Xfinity, Verizon, AT&T, etc. Could be network operators like a Cisco. Amazon AWS would fall into that camp. Google Cloud, Microsoft, etc. And then third-party DNS services such as Google Public DNS and Cloudflare DNS. These resolvers handle queries from many clients all the time, like they're very, very busy, and they perform the recursive lookup to resolve domain names. The trick here, the main thing you have to keep in mind is you cannot go directly to a machine with a name. You must hit the machine by IP address. So now we've come full circle. First of all, we have to go get the MAC address of the computer that we want to hit. Then we get its IP address. We know the IP address somewhere along the line. We have looked it up, and that's posted, and then we can hit that IP address. So you're hitting everything by IP address, not by domain name. Now, why does DNS caching exist? This is a very interesting idea. Probably 3 or 4 or 5, 7 people are sitting around having coffee talking about, wow, this DNS thing is slow. How can we speed it up? And the idea came that, well, you know, for very frequently hit websites that a client might have, Google is a good example of that, we'll just cache that. We'll keep that locally cached so that we can hit it much more frequently, much more quickly than if we just needed to go out and get the address every time. Caching is considered to be an auxiliary memory from which high-speed data retrieval is possible. The key here is high-speed data. DNS caching is a core feature of the DNS system. It saves DNS lookup results temporarily. Now, you got to hang on to that word because we're going to come back to that. In various layers of the network. Speeds up repeated lookups. E.g., if you visit google.com again, your device doesn't need to go through the entire DNS process all over again. It reduces load on the DNS servers globally, and it decreases latency. What is latency? You having to sit and wait for a response to come back is latency. Now, there are 3 or 4 different caching mechanisms. The first one is called browser cache. We've talked about that. Your browser hangs on to sites that you frequently hit. And I'm sure you can think about the sites that you go to every day, for example, Facebook, for example, maybe, or X, or Google, or Outlook, whatever. You're hitting these sites quite often. They're going to be cached in the local browser. Your operating system can cache these websites as well. And then you have the recursive resolver cache, like your ISP's DNS resolver, that has some of this stuff cached as well. So you can see how it sort of striates up the ladder, and then only if we have to do we go and hit a top-level domain server. And the reason we do that is because we don't yet know the number. Nobody knows that number yet. Now, we do want to talk about what's called a content delivery network. This is something that you personally could set up in Amazon, AWS, the other cloud environments support this as well. A CDN is sort of a one-stop shopping environment. It might be for movies or videos or file downloads. So that's why it's called a content delivery network. When we talk about something that you're reading or you're listening to, like a podcast, you're watching movies, you're looking at photos, that is content that is being delivered to you, and it is possible to set up what is called a CDN. You can do that very, very easily in Amazon AWS. The other cloud providers have the same sort of scenario that you can use to set that up. And caching is used internally in these environments. It could be that your corporation as well maintains DNS servers. That's where I got the most familiar with DNS, was maintaining DNS boxes that were local to the company that I was working for. Now, DNS isn't really a big pain to administer. It can have some gotchas from time to time, especially if you change IP addresses and DNS isn't made aware of it, for example. But it's actually not too bad. It's pretty easy to administer and to understand. When you get into the Windows Server Active Directory environment, there are more DNS entries that you might have elsewhere. But still in all, I would tell you that it's not rocket science to administer it, but you can get into trouble from time to time if things aren't all correctly hooked together. So you'll have to be aware of that. Now, I want you to know, I set this up way, way back in the day. Microsoft could see that it was going to be painfully slow to go out and surf websites by just the normal process. So what they developed was a thing called a proxy server, and this thing has caught on. Not Microsoft's proxy server per se, but the idea of a proxy box that's somewhere in your company that is serving up information on your behalf so as to speed up the process. And today it's also used to keep the bad guys out. And so you can see here that a proxy server was an extensible firewall and an integrated web cache server. And I only bring that up to show you that this stuff has been known about and has been around for a long, long time. Now, cached items do not stay there indefinitely. It's very important that you understand that. Every DNS record comes with what's called a TTL, a time to live, and this value tells how long in seconds a DNS record can be cached before it is considered outdated. The TTL value is set by the domain's authoritative DNS server. Now think about what that's saying. Who is it that sets the TTL? Well, in the case of Google, they would set the authoritative TTL value for whatever it is you're trying to hit. Now here's a couple of examples. The TTL is 3,600 seconds. That means that that DNS record is held for 1 hour. During that hour, any queries that will use the cached result. Well, the question is, what if during that hour something changed? Well, then that would be a problem, wouldn't it? So that's why you have to be concerned about TTL values. Now, if you're thinking about something like Google, which never goes down, is load balanced, we're never worried about it, the TTL can be quite a bit longer. But if we're worried about, a smaller domain of some kind, maybe we would be concerned about the TTL. And it is something that you should examine as you're looking at these things. You ping a host, find out what the TTL is set for. But basically it's telling you that that's how long it's going to be cached. Now, administrators must take into consideration the implications of caching and TTL. So the advantages are much faster browsing, less load on the DNS boxes, and reduced DNS traffic over the network. However, the disadvantage is it may cause delays when the record changes. So you change a host name, you change an IP address, you move it, whatever, you change domains, that could cause a delay. Users might see an old IP address, so you update to a new IP address, the old one is still in the old DNS range, and they're not going to be able to hit that site because they have the old IP address. Troubleshooting might require cache clearing. Yes, Very often, I don't know if you've noticed this, when you're out and you're trying to troubleshoot hitting a site, and you go to the web to look for answers, they might tell you to clear your web cache, because that's actually what's doing the deed. You've got the old data in there, you clear the web cache, re-hit it, boom, it refreshes, and now it's been recached and you're good to go. So there are some administrative things to think about. Now, I think I've told you the story before. A guy named Wayne, I worked on an IT team with him. He was a great administrator, very, very good, knew what he was doing. That dude spent 8 hours in a chair one day trying to solve a little DNS bugaboo. And it took him a long time, playing around, caching settings, all kinds of stuff, and messing around with the DNS servers. And finally, it took off. But I am not here to tell you that it's all easy peasy. You may wind up getting into a relatively serious thing as you're trying to troubleshoot DNS issues. So you need to be aware of it. What it means is that you need to be, especially if you're going to administer these servers, you need to be intimately aware of how DNS works, especially in the Windows Server environment, because it's a little bit different. Now here's a real-world example. Company changes its website server IP. Users whose devices or DNS resolvers, now remember, if a company changes its website server IP and they don't notify Xfinity, Xfinity's got cached data as well. It doesn't know either. At some point, you've got to go out and query an authoritative server. So users whose devices or DNS resolvers still have the old IP cached based on time to live might temporarily get errors on the old website. This is why low TTLs are used before you do a migration. So what you do is you go in and you deliberately lower the TTLs on everything so that things can time out a little bit more quickly, so the migration can work a little bit better. A short TTL, like 60 seconds, is useful for dynamic servers such as load balancers, content delivery networks, things like that, CDNs. A long TTL is used for stable, rarely changing services, i.e. mail.google.com, outlook.com, etc. But even then, sometimes they'll change things. They have to do a change of some kind. Now let's talk real quickly about DNS security. This is really cool. It's been heavily automated today, so it's a lot easier to use today. And the idea was DNS was designed back in the day when security wasn't a priority. Now, I will admit, even back in the Windows 2, Windows 3 days, Microsoft was just ridiculed for being hacked so often, and they really changed course. They've really done a good job. So they're not hacked nearly as often as they used to be. But security wasn't a priority back then, and now it is. So DNS works on trust. The servers reply to queries without authenticating the response. This makes DNS vulnerable to several attacks that can mislead users to fake or malicious websites, that can disrupt services by redirecting traffic, and by leaking private data through DNS queries. That is a big, intense subject for hackers. They love being able to hack DNS. Now let's talk about some of the security threats. This is slide 1, DNS spoofing. You spoof DNS so that a client thinks it's hitting, whatever, it's really hitting you. That happens very often. Attackers inject false DNS responses into the resolver's cache. Users can be silently redirected to phishing sites or malicious servers. And DNS tells your browser that google.com equals attacker's IP. That is DNS spoofing. Another one is a man in the middle, MITM. Please note, if you're going to sit for any CompTIA exams, they have changed from that phrase man in the middle to what they call on-path attacks. Just be aware that if you're taking a CompTIA exam and you see on-path attack, they're talking about a man in the middle attack. Attackers intercept or alter DNS queries and responses in transit. This is a really good area for you to go research. How do hackers intercept and alter DNS queries? That's a very, very good question to ask in your mind and get solved in your own mind how that works. when you're in like an airport or something like that, this is particularly risky. You're at a Starbucks or a McDonald's, or you're at an airport and you have public Wi-Fi that you're using. That could be risky for a man-in-the-middle or an on-path attack. Another one is DNS hijacking. So this is where attackers change the settings of your router or your device to be able to use a rogue DNS server. Now, in the Windows Active Directory server environment, you can't have rogue DNS servers. I'm not saying you can't set one up. You certainly could, but they are not part of the DNS transfer process that Windows Server does. So let's say that I've got two DNS boxes, one's in Chicago and one's in Atlanta, for example, and the zones are set up so I can do a zone transfer between the two. That zone transfer is secure and encrypted. You come along and you stand up a rogue DNS server. That will work until the security administrators find you, but it's not going to work to do DNS resolution in the Active Directory space. So it's something you need to think about. Hackers love this information. This is really, really a sweet spot for hackers, this whole idea about intercepting DNS. Every query goes through the attacker's server. It enables censorship, redirection, and or spying. There's another security threat. It's called exfiltration. Now that word might be new to you. It means the unauthorized transfer or extraction of sensitive information from a computer system or a network. We say that we're exfiltrating data, and you can do that with DNS. It used to be that you could log into DNS. If you could download the entire DNS database, put it into Excel, and off you go. Now you can't do that now, at least in the Windows Server environment. I'm sure Linux Server is set up the same way, so that it's really not possible for you to just exfiltrate that zone data today. But if it was, say, a dentist's office, a hairstylist's office, who knows, maybe you could grab that zone. And when you grab that DNS zone, the advantage you're getting is all of the machine names and all of the IP addresses that are on that particular network. So it's actually pretty cool information that you're getting as a result of that, which is why hackers love it. There are some DNS security technologies you should be aware. The big guy is called DNSSEC. So you go out and you register a domain name. Let's say you use Amazon AWS Route 53, or you use Hostinger, or you use Wix, or whatever you're using. You might, in most cases like this, large hosts allow you to register your domain via their capability. When you do that, one of the things that you might get offered is the ability to turn on DNS security. These are called security extensions. Very good, because what they do, they add a digital signature to your DNS records. It allows the resolver to verify that the response is authentic and not tampered with, so some rogue didn't get in there and tamper with the DNS entries. It helps prevent cache poisoning. What do we mean by that? We mean that we go in and we poison the cache. You think you're looking at Google, but we're actually redirecting you to a different server somewhere. Now, the limitation here with DNSSEC is that it does not encrypt the query. It only ensures integrity and authenticity. Now, there's another DNS security technology called DNS over HTTPS, lovingly called DOH or DO. And there's DNS over TLS, it's called DOT or DOT. These do encrypt the DNS queries and responses. That prevents eavesdropping. I can't listen to what DNS is doing. I can't do man-in-the-middle attacks, especially on public networks. DOH, or DNS over HTTPS, runs on port 443. Why is that? Well, because HTTPS natively uses port 443. So the DNS queries running DOH run on port 443. Now, the main thing to keep in mind, DNSSEC does not encrypt the actual query. DNS over HTTPS or DNS over TLS does do that. Now, DOT runs DNS queries over TLS port, which is different. It is 853. You probably want to commit these to memory. And then some common providers are Cloudflare 1.1.1.1, Google 8.8.8.8, and 8.8.4.4. There's a British company, I think they're British, called Quad9, and they use 9.9.9.9. Tips for IT pros. Use reputable DNS providers. I always did this. When you're setting up DNS, you can set up IP addresses that point to, first of all, your corporate DNS servers, but then second of all, you can point them to reputable DNS providers like Cloudflare. I put their address up here. Google Public DNS, I put their addresses up here. Note that they're both available in IPv4 and IPv6. I've given you the website addresses, and then there's Quad9, and you can see the IP address for that as well. So you have choices, and the way that it would work is number one and number two in the entry for your DNS addresses, I would put in your corporate DNS boxes, and then after that I would put in these well-known reputable DNS providers, and you can put in more than one. Now another thing I would do is use DNS providers that support DNSSEC. So this would be something like clean browsing. You can use this in your home side. It provides DNSSEC as well as DOH-DOT. Clean browsing also provides a family filter for you. And then there's one called NextDNS. This is a DNS as a service. So what they're doing is they're borrowing this from cloud notation, where I'm saying, hey, I've got customizable DNS as a service, and you can use this, and you can go with fully user customizable security and privacy settings. One of the good features of this is that you can disable the logs, which is great, but you can also provide strong filtering and tracking protection. And I gave you the website address for that as well. Okay, thank you for watching. Really appreciate you guys watching this. Very cool. There's a lot more to know about DNS. I really recommend that you jump right in there and get as much information, do as much research as you can. DNS and DHCP are the two workhorses in any network. You need to know about them. Name resolution, giving out IP addresses, very, very important for you to know. And so thank you for watching my videos. I really appreciate you watching videos, leaving comments for me. Please subscribe. Please tell others about my channel. I'm trying to grow the channel. And, if you've enjoyed this video, thank you, and you're welcome to leave comments. And I will talk to you in the next video. Have a super awesome, great spring day. Bye-bye.